Hello and welcome to this lab tutorial in our geospatial deep learning tutorial series. In this video, we will walk through preparing training data for modeling above ground biomass density using GEDI Level 4A dataset and Sentinel-2 data. So this is important because we are going to use this data for modeling above ground biomass using both the shallow artificial neural network and a deep learning neural network. Right, so to begin with, we are going to initialize Earth Engine, and then following that, we are going to import the libraries that we are going to use for this tutorial. Then after that, we need to prepare the variables. So before we do that, I'm going to import the area of interest. So this is the boundary for the project area. So for my case, I prepared this boundary in QGIS. So this is the boundary for Mafunga's Forest Reserve area in Zimbabwe. So you can prepare the boundary of your study area. Then you can import that boundary layer into Earth Engine, save the feature collection, and then you can always import it here. Right, after that, we are going to create a Sentinel-2 composite. So the composite here, we do the necessary pre-processing, that is doing the cloud masking. And please take note, for my case here, the composite is between January 2022 and April 2022. And the bands of focus here are from band 2 to band 12. So I've only selected 9 bands. And then I'm going to clip the composite to the study area boundary. Right, this is the display of the study area, and following that, I'm going to compute the vegetation indices from Sentinel-2. So I'm interested in normalized difference vegetation index, the soil adjusted vegetation index, and the red edge spectral index. So the red edge spectral index is calculated from the vegetation red edge bands in Sentinel-2. So hopefully these indices is going to give us more information on vegetation canopy that can help us to predict above ground biomass. So following that, we are going to measure all the predictor variables here. That is the Sentinel-2 bands and the vegetation indices. So please take note that these bands have to be in the same scale, or should have the same data type. So for this case, we cast them all to float 32. Right, next we are going to prepare the response variable. So this is the above ground biomass density, which is coming from GEDI Level 4A dataset. Okay, so this dataset contains above ground biomass density predictions in megagrams per hectare. So you can get more information from this link in Google Earth Engine catalog. Right, so this part is very important because first we need to define the dataset and do the necessary filtering in order to get a robust training dataset. So we start by defining the period of the dataset. So again, this is from 2022, but I just extended the dataset briefly to May so that I get many GEDI data points. Right then, so we are going to, as I said, we will process the GEDI level 4A dataset to filter and enhance the quality of the above ground biomass measurements. So this GEDI dataset is loaded from Google Earth Engine collection, and it consists of this monthly datasets of GEDI level 4A data. So here we are going to define 3 functions for masking or removing unreliable dataset, so that we ensure the data quality. So the quality mask here is going to select the highest quality dataset from GEDI. Okay, so and here we are going to use these 2 functions, the L4 quality flag and the grade flag quality, so that we get a high data quality. And next, we are going to use the error mask function. So this mask GEDI measurements with a relative standard error greater than 50%. Okay, so how do we calculate the error? So the relative standard error is calculated by dividing the above ground biomass density standard error by the above ground biomass density. So as you can see, this is how you calculate it. So we don't want here the error which exceeds 0.5. Okay, so we try to only get to remove, we don't want our measurements with a relative error, with a relative standard error that is greater than 50%. Right, then lastly, we are going to use the slope mask function. So this function is going to mask again the GEDI measurements on slopes greater than 30%. So we want to have measurements with slopes less than 30%. That is the whole point. So here we use the SRTM digital elevation model to do that. So this is very important because it allows us to get a quality data set. Right, so once we have used these filters to do the masking, we can create the visualization parameter so that we visualize the data set. So next, we are going to do the sampling. So we are going to sample the training points from the GEDI mosaic image that we created in the previous code. So each sample point captures the value of above ground biomass density from the GEDI band. Okay, so this is going to get it from the AGBD. So this is a above ground biomass density. So for importance here is the scale parameter. So the scale parameter controls the spatial resolution at which the samples are taken. Okay, so here the scale parameter 10 means that the points are sampled approximately every 10 meters. Please take note, this is very important. This parameter is very important because it defines the pixel size in meters so that we can use to generate the points. So if we have a small scale value here, such as 10 meters, this means that we are going to get more sample points from the study area. Yeah, so in contrast, if we increase the scale of value, for example, if we make it 20%, then we are going to have a kind of a coarse pixel. So that means we are going to have fewer sample points taken in the study area. So the small scale value here, which is kind of fine, is going to result in more sample points, while a large scale value, which is coarse, is going to lead to fewer sample points. So this is very important. So please remember this. Remember the relationship between the pixel size, that is the scale here, and the sampling intensity. Right, so if you want more sample points, that means you have to have a finer scale here. Right, so next, the geometry equals true ensures that the sample retains its spatial coordinates. So after sampling, we extract above ground biomass density points into an array. We want to, and then we calculate the summary statistics, so that we check how things are. Right, if we print this, we can see that mean above ground biomass is 44 megagrams per hectare. The median is 44, and then the standard deviation 28. The minimum is 6 megagrams per hectare, while the maximum is 271 megagrams per hectare. And we have about 50,664 points. Right, so next we can display these points, the sample points that we have derived from the GEDI mosaic. So this is the points for the project area. And we can also visualize the histogram and box plots of the sampled points. Again, you can see the distribution of the points here between around 8 to about 227. So from 6. And if you look at the box plot, it shows that we have a lot of outliers. So above 110, there are many outliers. And most of the figures, really, they are concentrated maybe between 10 here and 70 megagrams per hectare. Right, so this means that this dataset need to be cleaned, because most of the data points here, they are out of range. So this is very important to check. Right, so we are going to do the data cleaning. So for this study area, this is in the Miombo woodlands of southern Africa. So above ground biomass is usually between 0 and 90. This is according to a literature review. So I'm just going to simply filter the data points so that we are between 0 and 90. Right, and after that, we also display the data points, and then we also create an array, and then calculate the summary statistics, so that we visualize the data points. Right, after cleaning, now we have the mean is still around 40, and median 41, standard deviation is 22, and then the minimum is 6 megagrams per hectare, while the maximum is 89 megagrams per hectare. And we have this representation of the data points. So we can see that we have eliminated most of the outliers. Right, so our data is ready for sample, for creating a sample training data set. So what are we going to do next? We are going to create a sample training data set. So we will select the specific bands that we want to use for the data set. So remember, in our clipped collection, we have these bands, the Sentinel-2 bands, and then the vegetation indices that we want to use. So what we are going to do is that we are going to sample the values at the location of the training points. So first, we have defined a list of bands to be extracted. Okay, and then we will be sampling these selected bands at the location specified by the filtered points. So these are the points that we have cleaned. And then we create this training data. So this is the collection. So this is going to contain the response variable here, or target variable, as above ground biomass density. And I have just performed the sampling here at 50 so that we ensure that we have a good representation of the data set. Right, next, after finishing the sampling, we have created a kind of a table, right, that contains the data sets. So first we are going to export these data sets so that they are stored in a Google Drive. So I will start by exporting the Sentinel-2 predictors, that is the Sentinel-2 bands, and the vegetation indices. Okay, remember, this is coming from the merged collection of these data sets. So this is the image. This is why it's in GeoTIFF. Right, after that we export the table. So this contains the training data that is being extracted from the Sentinel-2 image and the above ground biomass mosaic from GEDI Level 4A dataset. Right, so this is in a CSV file because this is in table format. So we also export to Drive so that next time we can access this dataset from Google Drive. Right, so this is all about this step. So this step is very important. Please take note. If you want to have a robust dataset, you need to do a lot of data cleaning, and make sure that you understand the average above ground biomass density in your project area, so that you can filter the data sets and get a robust training data set. So thank you very much for watching this tutorial. See you in the next one.